Yeah, my name is Silvio Ricci. I'm from LCF. I'm part of the visualization and analysis team. I work with Joe Winsley, our team lead, and also Aaron has been a long-time collaborator. So the motivation for this talk is that we're exploring new solutions. Here at ALCF, our mission is to support and enable science. So currently, we have our production resources, Mira, an IBM VGQ supercomputer. And for analysis and visualization, we have a dedicated resource. That's Cooley GPU cluster. So we can do all our analysis and viz there. Now, with the new machines coming and transitioning to Intel architectures, we initially, at least, we won't have a dedicated visualization and analysis resource. So we will need to do everything on CPU or migrate our visualization and analysis algorithms there. So we want to support our users. We want to enable them to do some in situ workflows. And that's the motivation for this kind of work. So for that, we've been using the VL3 framework. This is parallel and scalable framework for visualization and analysis. That is, we started here in Argonne and the Computation Institute of the University of Chicago. So we've been working on this framework for more than a decade. And it started when the GPUs started to be programmable. It was possible at the time to do some of the stages of the pipeline started to be programmable. So we took advantage of that and created a GLSL render based on GLSL. VL3, essentially we run it so far on, or we scale it on visualization clusters based on GPUs. We can scale to the whole machine, and it can essentially render large data sets consisting of regular grids or particles. So the pictures here we're showing, the top picture is showing a data set generated here at Argonne. That's a turbulent flow data set. It's a 4K cube data set, meaning there's a regular grid of 4K elements per dimension. So it's 4K cube. We also have recently an algorithm for distributed advanced lighting. So that picture is showing that. VL3 is also good for streaming to large tile displays, and that's what the second picture is showing. And the third picture, Aaron already showed that as a hack data set. It's also a project running here at Argonne. This is particle-based, and we can scale. On this machine, we were able to scale using 128 GPUs. We were able to scale up to a full data set of 32 billion particles, which is half a terabyte. So essentially, the problem we're tackling here is raycasting volume rendering. And in this case, just to simplify things, you can see that the camera is actually the viewer there. And we actually cast these rays and sample the data along the rays. So one important thing to notice is that there's one ray per pixel. And also, we take multiple samples of the data. And that is what essentially impacts performance. The number of pixels and the number of samples we'll take of the data. So the algorithm tries to simulate essentially what light, the propagation of light physical effect. So since VL3 is based on, it was originally based on OpenGL, one of the possibilities for porting it to the KNL was to use this solution available from Intel called OpenSOAR. So it's essentially a replacement for OpenGL. You just compile it, build it, compile it, and it generates a library that you replace directly just using your LD library path environment variables. And so it works. And what and from this preliminary results, we'll be showing that it works. It works off the shelf. So it's purely CPU based, and they take advantage of AVX instruction sets. AVX2 so far, not 512, from what I know. That may change in the future. And it's part of the Mesa project. Most of you who are familiar with Linux should have seen the Mesa libraries around for software rendering when you don't have a graphics card. So these are some preliminary results of our tests with VL3. These are single node results. And the chart here will show in X, you will see the size of the data set, right? So the size of the data increases in X. So as expected, there will be more samples, and performance should go down a little bit because it's more demanding. The other thing, in the y-axis, you see frames per second. So in this case, it's the inverse of time, so the higher the better here. And frames per second is a usual metric in graphics. All right? So if you can achieve something like 30 frames per second, that means that your visualization is interactive, something that is highly desirable. So the results here you see in the also there's two curves, two charts here. One at 800 by 600 resolution, and the second it's 1080p. So there's more pixels and more rays to cast. So that means that performance should also go down a little bit on the second chart, and that's what we're observing. So the cards here, the first in blue is the GPU one, and GPUs are really good at ray casting, especially with this size of data. So we can achieve very good frame rates on a single node with this. But the other three curves, orange, yellow, and gray, are CPU renderings of the same data. And here, it's not optimal, but still gives us something usable. So the take-home message of this slide is that we're able to use it. We have an immediate solution to use on CPU, especially on KNL architectures, and still needs some optimization. The team developing this solution still hasn't done any work on KNL. So we hope that they will keep optimizing for KNL and keep improving this solution. So with this, I'll turn it over to Aaron, and he will discuss his result on using the second solution from Intel, which is Osprey.
Yeah, thanks, Silvio. So this is some work that I did just last summer to integrate Osprey's volume renderer into VL3. And as Silvio mentioned before, VL3 is a modular interface, and it provides already several rendering backends. So in addition to GLSL, there's a CUDA backend. A while in the past, before Osprey really existed or was easily usable, I developed something called IVL that was sort of a hand-coded vector intrinsic exercise with a little bit less of the pain. And that was an option as well. And then I added this Osprey option. And the code for this is actually amazingly simple. I was stunned by how easy it was to just drop Osprey into this. And you just have to write a little bit of code to get the transfer function and camera to match up. And then more or less you're ready to roll. And the same sampling rate, same parameters, maybe a few quirks, but nothing serious. So I think that's what's interesting is how Osprey is designed to make it easy for people to just drop it in and use it. With respect to the shader, you would write in GLSL in VL3 or possibly in CUDA in that kernel. And in Osprey currently, you have to actually go into the Osprey code and change or modify the raycast volume renderer ISPC kernel. But since that's all open source, anybody can do it. And I think it would be interesting in the future to have support for putting that directly in the VL3 code base and having Osprey somehow know about it. So I thought that was interesting. So the results, I'd say overall are more encouraging than what we were getting out of SWR, not because SWR is bad, but because it's really designed for fast rasterization, not for necessarily fast shader fragment fill type operations. So compared to my old IVL stuff, I'd say Osprey was roughly 3 times faster, but that's mostly because my old IVL intrinsics code wasn't really generating AVX512 intrinsics. It was probably generating AVX2 and maybe not even generating scatter gather instructions. So it definitely had some issues in just moving immediately to KNL. And what we find when we do a head-to-head comparison of Osprey VL3 versus GLSL VL3 is for small data that GPU is, and here I was looking at a 1080 GTX, so basically the latest and greatest consumer card that you can get. For small data, 128 cube, the GPU is probably several orders of magnitude faster. It's over 1,000 frames per second. But then somewhere right around the 1K cubed mark, so the 8 gigabyte to 16 gigabyte mark, the performance starts to narrow and it starts to move in favor of the CPU and Xeon Phi. Once you go over your PCI bus threshold, over your GPU memory size, then performance basically tanks, and you can actually do it. You can actually get data across the PCI bus and render larger things on the GPU, but you're really penalized performance-wise. You're at less than a frame per second, so the GPUs are just not an option really at that point for interactive performance. Whereas the KNLs and the CPUs, they're easily over 10 frames per second and pretty consistently interactive, which I think is important. And the last thing to note about this chart is that I compared the KNL Xeon Phi to a very, very nice Xeon workstation. 72 core, 3 terabyte of memory workstation, which probably in the market would go for anywhere from $50,000 to $70,000. So this is not like an apples to apples comparison of KNL versus Xeon. This is KNL versus very, very nice Xeon. Yeah. So in conclusion, yeah, the GPU is fast, really fast for small data, and KNL and Xeon are fast for larger data anytime you're really out of core. And I'd say right around the 8 gig data set mark, that's when they're more or less in the same ballpark, maybe off by a factor of 2, depending on what your GPU is and how much memory you have. What I like about VL3 is that for the most part, we're doing brute force volume rendering without any major optimizations. We're not using early termination or space skipping or really opaque data sets. This is as close as we could get to sample for sample to do this comparison. And obviously, once you start to look at different data where there's a lot more adaptivity, you can play more clever tricks with your algorithms, and the story might change. Yeah, in future, I think we'd be interested in how this behavior extends to parallel, doing a weak and strong scaling study and exploring other rendering modes that are already supported by VL3, such as particles. And yeah, otherwise, Silvio and I will be happy to take questions.
Comment on some important differences, that first one about versus naive shared 3D arrays. Is that something that you need to improve, fix, or it's just how it is?
Silvio, or should I? Yeah. So in Osprey and in the open SWR implementation, there is no hardware 3D texture interpolation on the CPU. So you have to hope that it generates, first of all, SIMD code with scatter gather, and that scatter gather actually preserves vectorization once you actually get your data back. So that's really the best you can do on CPU and Xeon Phi, because there is no built-in 3D texture interpolation. So that's something where GPUs, depending on how you look at it, it's either a built-in unfair advantage or a built-in fair advantage, but that's structured volume data is something they have been designed to do for a very, very long time, like 3D textures. But yeah, I think maybe it's worth noting that in the Osprey implementation, it uses ISPC, so it's all vectorized, it's all using scatter-gather. Probably should be similar in OpenSWR, it's just I'm not sure how it's load balanced, or I mean in that case it's Clang generating,
Right,
or LVM generating that code.
First thing to say is that OpenSWR has been optimized for geometry, right? And not for this kind of work. So it's surprising that it works right away.
Yeah, yeah. Good question.
So these visualization softwares are designed to load results of an application. Is that correct? Kind of. Is that how they work? I mean, what are you visualizing?
That's correct. Yeah, we get data generated by simulations.
So what kind of simulations, what kind of application do you support? Like, what can you use to visualize the results from, like, using that? Just want to know.
For VL3 specifically, it can load data that is regular grid, like meaning like XYZ with densities or another scalar values there. It can also use particles for particle-based simulations, and we recently connected to other molecular dynamics simulations so we can visualize atoms.
Thank you.
Who was first? Okay. Go ahead, please.
Okay, so you mentioned using this ISPC compiler.
Yeah.
I mean, that sort of thing kind of sounds like something that, is there some sort of convergence of programmability of GPUs and CPUs on some standard?
The million-dollar question. So ISPC came along, I'd say a few years ago. It was originally developed by Matt Farr when he was at Intel, and a few other people, and then it ended up getting productized and turned over to a more or less permanent team at Intel. ISPC, I think of this as sort of the SPIMD tasking model. It's kind of similar to OpenCL and CUDA, but in a sense, it's more specific to graphics type workloads where you don't really end up doing any sort of reduction of your data ever. You only ever want SPIMD tasking. It's very, very good at that. It really uses LVM under the hood and spits out consistently vectorized code. I'd say it's less clunky to use than OpenMP, and you know what you're getting is the advantage that ISPC has. The disadvantage is that I don't see it really replacing OpenCL or OMP SIMD and OpenMP for a lot of more general programming model use cases. It also doesn't support templates, so there are a lot of CUDA codes that you can't just naively port to ISPC. So that's a disadvantage. But if you're doing this type of work and you want it to be fast and guaranteed performant, then it was the best solution that we and the Osprey team could come up with.
Are you planning to support visualization for adaptive mesh refinement data structures?
That might VL3 or Osprey.
Combo, BoxLab.
Don't right now, but yeah, we're always open to supporting applications, specifically inside applications running here. So yes.
VL3 had some AMR support, but yeah.
It's got some AMR support, yes. We need to revisit that part, but yes.
Osprey has tetrahedral and hexahedral mesh support for AMR data, but not what I would consider block structured AMR. There's some research that's being done there, but it's not. It's still at the research level and not the production level. But if you have data and you'd like to work with either or both VL3 Osprey teams, then we would be very interested.
Both Aaron and Silvio for this presentation.